Hello, welcome to Chapter 3, Section 4. Today we talk about concavity. So concavity is really just asking, like, is it concave up or concave down? You might remember from back in geometry, concave and convex were like two different types of shapes, or like the way that the shape was curved. So we focus only on concavity, so concave, and we just look at whether it's concave up or down, talking about our graphs. So the graph of f of x, the original function, not the derivatives or anything, the original function is concave up if it kind of curves like this, or this. So those are all considered concave up. And so looking at the shapes, it's kind of like if it's curving upwards, I guess, is like the best way to describe it. Where the curve itself kind of like, think of like a scoop, you can scoop water out of it. If you were to scoop and look at that graph, would it hold water? But then concave down would be, no, you can't hold the water because it's curving downwards. Or like the curve itself is facing downwards. So these are all examples of concave down because you can't hold the water in it. So like mathematically, the definition would be that the function lies above the tangent line for concave up. And what that means is, like, for any of these curves, if I were to draw a tangent line at any of the points, so let's say we were to draw at this point right here, its tangent line, remember that's the line that only touches at that one point, would be somewhere like that. And so that tangent line would be below the function. So the function lies above the tangent line because it's on top of it. And so the opposite is true for concave down. If I were to pick any of these graphs or these curves, pick a random point and draw a tangent line, this time the function itself, that curve, would be below the tangent line because it's underneath it. So that's like the mathematical definition. We can even go like equation style mathematically. The definition would look like this. If we were to look at the second derivative of f of x, so remember double prime means second derivative. If the second derivative is a positive number, then that means at that point it's concave up. If the second derivative is a negative number, meaning it's less than 0, then it would be concave down at that point. So with concavity, much like how we did with the increasing and decreasing intervals, we want to be able to state what intervals is the function going to be concave up and what intervals is it going to be concave down. So it's going to be a kind of similar process. So let's do some examples. Okay, so we're going to be determining the open intervals on which the graph is concave up and concave down for the graph of f of x equals negative x cubed plus 7x squared minus 15x. So, like we said with our concave up and concave down definitions, we want to figure out whether the second derivative is positive or negative. So our first thing that we need to do is find the second derivative. So first let's start by finding the first derivative. We can just use the power rule here because we have a pretty straightforward polynomial function. My first derivative is going to be negative 3x squared plus 14x minus 15. Okay, got the first derivative down. Second derivative. If we take the derivative of our first derivative, then we get negative 6x plus 14. Okay, so at this point, we have the second derivative. We want to basically figure out if we set it equal to 0, then we can tell when it changes from a positive to a negative concavity. So it's kind of like finding our critical points, except for our second derivative, it's not called critical points, but it's kind of that same process, because with critical points, we would find the first derivative and set that equal to 0, solve for x. So here, we're just doing it with the second derivative. And I'll tell you what the name for this is in a little bit. So I'm going to set the second derivative equal to 0, and then solve for x. So if I subtract 14 on both sides and then divide by negative 6, I get, and reduce, 7 over 3. Okay, so it's like our critical point, but it's not really a critical point. But we're going to do that same process with the number line here. So I only got one value of x, so that's all I'm putting on my number line. And then just like with our intervals of increase and decrease, I'm going to test out the numbers that are around this value that I just got, the 7/3. So like I could test out 0 and 3, let's say. So when we test it out, we're going to plug it into our second derivative, because remember, we're trying to see if the second derivative is going to be a positive or a negative number. So when I plug in 0 into my second derivative, I end up with -6 times 0 plus 14, which is positive 14. So I'm going to get a positive number over here. And then on this side, let's just plug in 3. And again, you don't have to choose 3. You can choose any number that's bigger than 7/3. I end up with -4, which is a negative number. So that means, with my plus and minus here, that means my second derivative was positive when we were less than 7/3. So that means that section is going to be concave up. The negative side would be concave down. Okay, so writing this out nicely, we have intervals of concave up from -infinity until 7/3. And then concave down would be from 7/3 to positive infinity, everything to the right. That's kind of it for concave up and concave down intervals. So earlier I said I would tell you what that number 7/3 was actually called, because it's not a critical value. So anytime that you have concavity changing directions, going from like plus to minus or minus to plus, this number right here is called a point of inflection. So a point of inflection, or sometimes you might hear it called an inflection point, is when the concavity changes. So when you see like from plus to minus or changing from minus to plus. So that's how you identify an inflection point. So recapping what we've done so far, if we are asked to find points of inflection or to find inflection points, what you want to do is find the second derivative, set it equal to 0, and then solve for x. Then do the number line thing. Test out the numbers around it, and then see where it changes from plus to minus or minus to plus. And so that's kind of the process for both finding your intervals of concavity and for finding points of inflection, because you're going to find the second derivative, set it equal to 0, solve for x, and then do the number line. So from our previous example here, because on our number line we go from plus to minus, for 7/3, that's going to be our inflection point. So let's do another example. All right, this time we are going to do both things, identify points of inflection and find those intervals for where the graph is concave up and down for the graph of f of x equals -4e to the -x²/8. So slightly more complicated of a function here, just so we can, move away from the basic derivatives. Okay, but like we said before, first thing we need to do is take our function and find the first and second derivatives. All right, so for our function, we've got -4 as a constant being multiplied to e to the -x²/8 power. So I'll just start with the -4. It's a constant being multiplied, so that'll have to stay there. And then the e to the -x²/8 power, that requires chain rule, because technically we have like a really complicated exponent. So our inside function is the -x²/8. And so the outside is e to all that stuff. Well, the derivative of the inside is going to be, let's see, it's a constant of -1/8 times x². So the derivative of x² is 2x. And then the derivative of the outside is just e to whatever power, because e to the x power, the derivative is just itself. Okay, so derivative of the outside times the derivative of the inside is going to be e to that stuff, x²/8, times the derivative of the inside, which is negative 1/8 times 2x. And then simplifying this out so it looks a little nicer, I think I can, all the constants kind of cancel out because they multiply to 1, and then I'm left with x e to the negative x squared over 8. Just kidding, it's positive because we had a negative times a negative. Okay, so from here, we just want to find our second derivative now. So because I have x times e to the negative x squared over 8, I have things that are being multiplied, which means this is going to require product rule. So for my second derivative, I'm going to need to find the derivatives of each of those parts. So the derivative of x is just 1. The derivative of e to the negative x squared over 8 is, we just found that, e to the negative x squared over 8 times the negative 1/8 times 2x. That was the derivative of the outside times the derivative of the inside. Okay, actually, I'm just going to rewrite this so that it looks a little nicer, because it's really just negative x over 4 power. Okay, or sorry, no, negative x over 4. There's no power. All right, product rule. So remember, that's the one where we kind of like cross multiply. So multiply those together plus those multiplied together. So we end up with e to the negative x squared over 8 times 1 plus x times e to the negative x squared over 8 times negative x over 4. Okay, let's simplify this out a little bit, because that x and the negative x over 4 at the end can multiply together to get negative x squared over 4 e to the negative x squared over 8 power. Okay, so there's my second derivative. Once we have that, we want to set this equal to 0 and solve for x. And because we're solving something kind of complicated, probably the easiest way to make this look nicer is to factor, because I see both terms have an e to the negative x squared over 8 power to it, so I can factor that out as a greatest common factor. So that'll leave me with 1 minus x squared over 4. Okay, and then once you have things factored, you just set each of your factors equal to 0. So e to the negative x squared over 8 equals 0, and 1 minus x squared over 4 equals 0. So solving out our two equations, with our first one, e to the negative x squared over 8 equals 0, for this equation, we're basically trying to think of like what can you raise e, what exponent can you raise e to get 0? And if you think about it, there's nothing, because e to any positive number is just going to be like some number, not 0. E to any negative number is just going to be a fraction, because an exponent that's a negative is going to make it a fraction. And so there's nothing where it actually equals 0. And if you think about the graph of e to the x power, it doesn't ever reach 0 because there's an asymptote there. And so for this equation, there's no solution. So nothing out of that one. So let's solve our second equation. 1 minus x squared over 4, I can add x squared over 4 to both sides and then multiply both sides by 4. Square rooting both sides gets me x equals plus or minus 2. So with those two numbers, those are my potential inflection points. So at this point, we want to make our number line with those numbers there. I say potential inflection points because we want to make sure that like it switches from a minus to a plus, or a plus to a minus before we can actually say that they're inflection points. Okay, so let's choose our numbers to test out. And remember, when we're testing them out, we need to plug it into our second derivative equation. So that was this one right here. Or you could even do the factored one. You're going to get the same thing. So remember, when we're plugging it in, I don't actually care about what number I end up with when I plug it in. I just need to know if it's positive or negative. And so plugging in my negative 3, remember e to any power, it's always going to be a positive number. It's either like e to some power, or e to the, like a fraction. So always positive. And then minus x squared over 4 times that same positive number. So really we just need to figure out if negative 3 over 4, or negative 3 squared over 4 ends up multiplying to become a positive or negative number. So plugging everything in, I end up with minus, plus, minus. I'm not going to plug things in for you. You can do that on your own. I have great faith in your abilities. Okay, so once we have our signs, then we know anywhere where it's negative, that's going to be where it's concave down. Anywhere where it's positive is concave up. And because at negative 2 we go from a minus to a plus, that means negative 2 is an inflection point. And at positive 2 we go from a plus to a minus, so that's also an inflection point. So here it is all written out. We've got inflection points at x equals 2 and negative 2. We're going to be concave up between negative 2 and 2 because of that positive section right there, and then concave down from negative infinity to negative 2, and from 2 to infinity because of this negative sections there. Okay, one last thing that I want to talk about in this section then. So the last thing I want to talk about today is called the second derivative test. So it's called the second derivative test because it's similar to the first derivative test that we talked about last section. So basically it's just another way of finding maxes and mins, except instead of using the first derivative, you're going to use the second derivative of your function. To use the second derivative test, what you want to do is find your critical points first. So that's the same as the first derivative test. Remember, to find your critical points, you're taking your first derivative, setting it equal to 0, and then solving for x. So when you solve for x, these are your potential mins and maxes. You just don't know which one they are. So that's why you want to find those first, because then we can test those numbers out to see if they're maxes or mins. Set up your number line like you would for the first derivative test. But then, instead of plugging in the numbers that are around your critical points, you're actually going to plug the critical points into your second derivative. So I like this method better because there's less things for you to plug in. Because when you plug stuff in that's around your critical points, there's actually one extra thing to do. But if you just plug in the critical points into the second derivative, then there's less plugging in. If you end up with a negative number, then that means it's going to be a maximum. If you get a positive number, then that means it's a minimum. If it's 0 when you plug it in, then it's inconclusive. So that's the only bad thing, because if you end up with 0, which doesn't always happen, but who knows, that means the second derivative test doesn't actually work. But if you think about it, if you're plugging into the second derivative, it's telling you whether things are concave up or concave down. So when you get a negative number, that means it's concave down. And so if you have something that's concave down, like curving downwards, then you're going to have a maximum there because it's like the top of that curve. If you have something that's concave up, because when you plug into the second derivative, you get positive, then it'll go, oh gosh, I can't even use my other hand. This way? It's hard to hold my arm this way. Okay. And then you would have a minimum because it's like the lowest point of that curve. Okay, so I'm going to use our first example to use the second derivative test to find any relative extrema. So following our steps here, we want to find our critical points first, which means I am finding the first derivative and setting that equal to 0. So our first derivative was negative 3x squared plus 14x minus 15. And I'm going to set that equal to 0. And then we want to solve for x. So I've kind of sped up the process here. After setting it equal to 0, I multiplied everything by negative 1, so that way I don't start off with a negative term. And then I just factored solve for x. So those are my critical points. So we're going to use that now in our number line, or those numbers in our number line. So 5 over 3 would come first, and then the 3. And then we would need our second derivative, which earlier we said was negative 6x plus 14. And so these two numbers, the 5 over 3 and the 3, those are the numbers that we're plugging in to the negative 6x plus 14 as our second derivative. So when I plug in 5 over 3, negative 6 times 5 over 3 plus 14, I end up with 4, and when I plug in 3 into my second derivative, I end up with -4. So my 5/3 ended up with a positive number. When x equals 3, I end up with a negative number. So if the second derivative is positive, as it is with the 5/3, that means this at x equals 5/3, it's concave up. So that means this point is a minimum. And then at x equals 3, I get a negative number for the second derivative, so that means it's concave down, which means this is a maximum. So far I have the x values of my minimum and maximum. To find the y value, I would just need to plug these two numbers into the original, and then that'll give me my actual minimum and maximum values. Because right now all we have is like where they occur. So doing some quick math, plugging in my two x values into the original function, I end up with these y values here. So for the minimum, I end up with a minimum value of -275/27 when x equals 5/3, and a maximum occurs when at -9 when x equals +3. That's it for this section. Thanks for watching. Don't forget to like and subscribe. Bye.